In this video, I'll show you how to solve the ALEKS problem called calculating vapor pressure from boiling point and enthalpy of vaporization. This is the equation that we're going to use to solve this problem. This is a bit of a beast of an equation, but it's actually going to be pretty simple. First thing that we're going to do is go through and identify as many of these variables as we can from the problem statement. So it tells us that we're working with substance X. Its enthalpy of vaporization, that's the delta H vap, is 27 kilojoules per mole. So we're just going to make a little note here. This is our enthalpy of vaporization, 27 kilojoules per mole. And I'm going to tell you right off the bat, that needs to be converted into units of joules per mole. I'm going to do that by multiplying by 1,000. So 27,000 joules per mole. That is our delta H value. Now the value of R in this equation down here, this is the ideal gas constant, as you probably know. And we want to use R in the form 8.3145 joules per mole Kelvin. The value or the units of R, that's why we needed to do this kilojoule to joule conversion up here. So it tells us that the normal boiling point of this liquid is negative 33 degrees C. Normal boiling point, that phrase normal boiling point, that means the boiling point at a pressure of equal to 1 atmosphere. So that term normal doesn't mean regular. Normal is referring to the boiling point, or referring to the condition of pressure being equal to 1 atmosphere. So this is telling us that when the pressure is equal to 1 atmosphere, the boiling point, the temperature, is negative 33 degrees Celsius. And as you can probably imagine, looking at the units of R, that temperature is going to need to be converted into kelvins. So let's go ahead and do that. 273.15 minus 33, that is going to be 240.15 Kelvin. And so that's going to be one of our pressure and temperature variables. It's asking us to calculate the vapor pressure. So this is going to be the thing that we're trying to figure out. We're trying to figure out a new vapor pressure at this new temperature of negative 57 degrees C. You probably guessed it. We need to also convert that into Kelvin. 273.15 minus 57 is 216.15 Kelvin. So from all of this, we can see that we know the value of delta H right there. We know the value of R. We've got two temperatures. We've got one pressure, and our unknown is the other pressure. Now, we're going to need to match. You can see we've got P1, P2, T1, and T2, and we need to match those up. So both of these, pressure and temperature, these both need to be P1, T1, or they need to be P2, T2. The subscript needs to match. These ones also need to match. To make this problem easy, mathematically easy for you to solve, we are going to want our unknown to be up here in the numerator. So this is just boiling down to math. In order to make this math problem easy to solve, we want our unknown pressure to be up here in the numerator. It's just going to require us to do a little bit less algebra. So we're going to make this our P1, and we're going to make this our T1. This is going to be our P2 and our T2. And it never matters which one we choose to call 1 versus 2, as long as we're consistent, meaning that we're keeping the common pressure and temperature variables together. So now that we've got all these variables identified, we can go ahead and start plugging stuff in. Our P1, that is our unknown. I'm just going to keep calling it P1. And the P2 is 1 atmosphere. And that is going to be equal to, we've got this exponential function here, the enthalpy of vaporization in units of joules per mole, not kilojoules per mole, 27,000 joules per mole, over the value of R, the ideal gas constant, in the 8.3415 form, 8.3145 joules per mole Kelvin. And then all of that, and this is all of this is up in the exponent of E. So we're all still up in the exponent. 1 over T2 in Kelvin, that's 240.15, minus 1 over T1, also in Kelvin, 216.15. And we're definitely going to need a calculator to do this. So to solve this in the calculator, I'm going to begin by solving this portion, and then I'm going to bring this piece into it, and then I'm going to do all of it to the E, and then we're gonna go from there. Okay, so again, I'm just gonna start with this portion. That's gonna be 1 divided by 240.15 minus 1 divided by 216.15. So that again is this math. And now I'm gonna multiply it and divide it by these other two numbers here. Multiplying it by the 27,000 and dividing by 8.3145. So I've done all of this math right here. Now that number that I just got, the negative 1.5 on my calculator, that is my exponent. So I'm going to do e to the answer. And now that is this whole entire right-hand side of this equation. So I'm going to rewrite the whole thing. P1 over that pressure, 1 atmosphere, is equal to 0.2228. And I left my Kelvin units off my temperature. There's no units at all on this number right here. So as you can see, the reason I wanted to choose the variables the way that I did is because to solve for P1, all I have to do is just this cross multiplication. It's extra easy because that bottom number, the value is just 1. So for my cross multiplication, P1 is equal to 1 atmosphere times 0.2228. I don't even need the calculator for that. My answer is, to two significant figures, 0.22 atmospheres.